Let us continue with chapter 5 today. Today we're just going to look at two very short and simple questions. These are the final answers for today's questions. Questions 1. A square frame of 20 cm by 20 cm is wrapped with 250 turns of wire. The total resistance of the coil is 250 ohm. The coil is situated in a uniform magnetic field where the plane is perpendicular to the field. A. Determine the magnitude of the induced EMF in the coil when the magnetic field is changed from 0 Tesla to 0.6 Tesla in 0.75 seconds. B. Calculate the induced current generated when the field is changing. To determine the magnitude of the induced EMF, again, I would like to sketch a diagram. So since the plane is perpendicular to the field, this is the diagrams that we have right now. So as you can see here, the plane of the coil, it makes a 90 degree to the magnetic field. So again, why do we need a diagram? Well, in order to calculate the magnitude of the induced EMF is equals to negative n d phi over dt, where phi is equals to BA cos theta. And again, this theta is the angles between vector A and vector B. So to make it easier for us to determine the angles between vector A and vector B, I would always encourage my students to sketch the diagram, especially if they are not perpendicular to each other. So now let us go back to the diagram. Where is the directions of the vector A then? Remember, vector A is not the cross-sectional area of the coil. It is the vector that is perpendicular to the cross-sectional area of the coil, which is perpendicular to the plane of the coil. So in this case, we have A pointing to the right-hand side. And based on the diagram, the angles between A and V is equal to 0 degree. Now that we have the angles between vector A and vector B, let us proceed to the calculation. Step 2, apply induced EMF equations. So induced EMF for a coil is equal to negative n d phi over dt. Expand the equations. We now have induced EMF equals to negative n d BA cos theta over dt. It can also be written as negative NA cos dB over dt. Why? Well, because according to the questions, the variable that is changing is the magnetic field. Therefore, we keep it as dB, which shows that the B is changing. Now, there's one thing that you have to take note. A is not always equals to pi r squared. In these questions, you are given a square frame. Therefore, for square frame, A is equals to L times L, where L is the length of the side of the square frame. So substitute the values into the equations, you will then get EMF equals to negative 8 volt. But remember, the question is asking for the magnitude only. In this answer, the negative sign has nothing to do with the magnitude. It just simply represents the direction. It shows you that this induced EMF is always opposed to change that you make onto the coil. Therefore, the final answer for this question should be the magnitude of induced EMF is 8 volt without the negative sign. Questions B. To calculate the induced current, you just simply apply the equations V equals to IR. So EMF induced is equals to I induced times R. Rearrange the equations and then substitute the values into it. You will obtain I equals to 0.032 ampere. Questions 2. A 60-turn rectangular loop of 200 cm square area is rotated in a magnetic field of 0.02 Tesla at an angular frequency of 120 pi radian per second. Determines the maximum value of the induced EMF in the loop. In these questions, you are given a rotating coil. So to calculate the induced EMF in the rotating coil, you just simply apply the equation for induced EMF in rotating coil, where induced EMF is equals to NBA omega sine theta. Now it is up to you whether you want to use the equation with sine theta or sine omega t. Why? Because the question is talking about the maximum value. When you're looking at maximum value, this part is always equals to 1. So in this question, I'm going to substitute it as sine 90 degree because it will give me 1. So substitute the values into the equations and you will obtain induced EMF equals to 9.05 volt. So that's all for today. I will see you again tomorrow.